kind of get through this year. There's 2 weeks from now, Scott's doing a talk, and you're talking about what's known in science.
Yeah, science facts that you may have wrong.
And there are a few of them.
Yeah.
I don't know if we got enough time for you on that. So,
I can give you a preview.
science facts that you may have wrong. This seems like it's echoing a bit, Dave. I don't know if it's too loud, or does it sound okay, or a little loud? Okay.
Like that, we only use 10% of our brain, right?
Yeah.
A lot of us grew up hearing that. So that's just one of several I want to.
I use all my brain, but mainly for ballast.
Yeah, I use mine to keep my pillow warm. Yeah, right.
So that's 2 weeks from now. We were talking about Green Sanctuary coming in and having a talk, but I guess they don't have their people lined up for exactly that. So I think I'm on deck for 4 weeks from now with a talk, and they'll have to plan and get organized by that time. And then finally on 17th, I think Jim, what's his last name, Scott?
Walter.
Jim Walters, a PhD and associated with UIC, emeritus professor, and he's talked a couple times here about evolutionary psychology. This basic theory put out by a guy named Reed that a lot of ways that people act now, how we act now, are based upon how the years and years of evolutionary development that came into our minds over the years. He's talked a couple times if you've been here for it. He's pretty entertaining. It's interesting talk. So I think he's going to talk, and that's somewhere around the 16th or something like that. You're going to be out having Christmas in California, huh? Yep. Okay. All right. So good. We're starting to fill up. John's here, so we can start. And Jim came up and talked to me. Jim Honneberg came up and talked to me and mentioned that he's a geologist, 26 years working for the EPA and working with oil and gas interests and so on. So he is very interested in paleoclimatology and climate change and so on. So I think it's going to be a very interesting topic. We've touched on a few of these issues before with climate change and talk, but there'll be time for comments and thoughts and questions as he finishes up on it. So that's what's coming up the rest of this year in Science Sunday, and then we'll start out again after the new year starts. So I'll hand it over to Jim, and you can get started.
Thank you. People probably haven't heard that term before. I hadn't either. What it means is it's ancient climate, what it means. The study of ancient climate. But I'll be, oh, oops, shit. Crap. Excuse me. All right. Anyway, today I'll talk about Earth history and how climate fits into that. And then I'll also talk a little and outgrowths from that in terms of extinctions and what the future might hold. This is, my mom would call this slide busy. It's not a great slide, but I wanted to show the history of the Earth in one slide. And this shows that Earth formed about 4.5 billion years ago, and life started up about 3.5 billion years ago. And then we had, I'm going to talk about the snowball Earth, which I thought was kind of interesting, and then how life then took off. And we're here the last million years, humans. Oh. Oh, there we go. The early Earth, as I said, it formed about 4.5 billion years ago. And before that, just before that, a planet-sized object hit the Earth, and that formed the moon. And the Earth then formed, and it has a core mantle crust, and the core is iron nickel, and it has has an outer crust, which is liquid, inner crust, inner core is solid iron. And I mentioned before, life started about 3.5 million years ago. And of course, out of the formation of the Earth, we had oceans and atmosphere, and we had very low oxygen for a long time. Oops, not doing well with this. Oh, up there? Oh, okay. Anyway, about 700 million years ago, this is a new idea which I hadn't heard about until recently, but the snowball Earth occurred where the Earth froze over completely. It's like total ice over all the Earth. And some people think it's more of a slush ball Earth, not a snowball Earth. The difference is the slush ball Earth still had a little bit of water. And some people think that that would be needed in order to continue life. But most people would say it was totally frozen over. And the way this started was we had low carbon dioxide concentrations, and because of that, you began to form glaciers, and what happens is it started to feed on itself, and that ice reflects 85% of the sunlight, whereas water only reflects about 10%. So you've reflected a lot of sun energy, and that caused the basically glaciers to take over. And once it hits 30 degrees latitude, there's no stopping it. It's going to keep going. And one thing that resulted at the end of it was what we call the Great Unconformity. And I'll talk about that a little bit later. Oh, anyway. Evidence for this event is what we call drop stones, which I hadn't heard of before, but what they are is they're big boulders found in a mud matrix. And the only way that can happen is from glaciers. And people have looked at these in the modern, in Alaska, and they found that, yeah, you have this mud outfall with big stones and rocks. And the only way that can happen is from glaciers. Because like a stream, you'll have sorting, and you will not have just mud with just big stones. And a guy did look at this, found it in the ancient in Australia, and that got him thinking about snowball Earth. And the other thing that happened is that some evidence for it is what we call striations, which is basically scratches in rocks from glaciers, where they drag pebbles over the rocks and they scratch it. I'll show you a picture here. And this is a drop stone, and then these are striations, kind of scratches in rocks. They go in the direction of the flow of the glacier. And this also shows snowball Earth deposits above it. Oops. Oh, going the wrong way. Oh, jeez. This is another picture of a guy who has these videos on on YouTube. His name is Myron Cook. This is from one of his videos. You can see the big rock here in this mud matrix, along with some other big stones. But he has really good videos about different geologic events. Oops, snowball Earth ended about 600 million years ago, and life barely survived it. And what happened, which caused the snowball Earth to end, was you had lava flows, and you had, with the lava flows, you had emissions of oxygen, and of course, directly from the flows too, you had the heat melting the glaciers. Yeah, the Precambrian, which is like more than 600 million years, we had low oxygen, and you had iron deposits, which actually I have a chunk of it here. It's called banded iron formation. And it's heavy. And it has interbedded layers of red quartz and hematite, which is an iron-rich mineral. Anyway, I kind of digress a little bit, but I thought that's kind of cool. It's my favorite rock. I found that up in Upper Peninsula in Michigan. And anyway, once the snowball Earth melted, you had a lot of oxygen being developed, and life really took off at that point. And they think the reason you had a lot of oxygen occurring, besides the lava flows, you had these little organisms called cyanobacteria, and that created a lot of oxygen. The little bacteria extrude a lot of oxygen. And this is the concentrations of oxygen from the beginning of the Earth and to snowball Earth was about in here, and then oxygen really took off. And with oxygen, you were able to develop a lot more life. And one thing I thought was kind of interesting here is that, if you notice here, there's a peak here, about 35% oxygen was happening in the late Paleozoic, like 400 million years or so. But what happened, well, right now, we're down to about 20%. But what happens with the high oxygen content is insects can be really big. So you had dragonflies like with a 28-inch wingspan. So I thought that was kind of interesting that would, and the reason is because I found out that insects don't have lungs. They have little tubes that absorb the oxygen, I guess. And that's why if you have a lot more oxygen, you can have bigger insects. If the oxygen goes down, then the insects get smaller again. And this is just a photo of that piece of rock I'm handing around. This is the outcrop, which is a cool outcrop up in the Upper Peninsula, Michigan.
That's where a lot of iron mine.
Yeah, the iron content of that rock, the banded iron formation, is 30%. So it's definitely ore grade, and they mine that up in Michigan. 30%, 30%. And that was on the Edmund Fitzgerald when it went down, their little pellets that they made from the rocks.
Can you talk more about the colors, what the colors are?
Oh, sure,
how they
yeah.
get there?
Yeah, the red, daggone it, shit. Anyway, I hit the right button here. The red bands are chert, which is a iron-rich quartz. And the silvery stuff is specular hematite. It's a mineral that's very high in iron. So they're banded, and they got folded and all this kind of stuff in the outcrop. It's pretty cool. If you ever have a chance to get up there, it's in Ishpeming.
Is that from lava flow or from?
No, it's from precipitation in oceans. And the low oxygen allowed the precipitation to occur. When you have higher oxygen, like now, you can't have that because the iron then would be oxidized. But back in 2.5 billion years ago, which is how old that rock is, you had iron being precipitated out of seawater. And they think that the bands represent annual events. Geologists have a lot of theories about things. And this is just a graph showing the oxygen content over time. You can see, I'm not oxygen, this is temperature. And one thing that this shows is that in general, the temperature is actually higher than it is now. Right now, we're down here. So we're technically in a ice age. But in the past, the temperature was actually higher. And this is just evidence for how we figure out what the temperatures were then. One of the big ones is isotopes, oxygen isotopes and other things too. But there's a lot of evidence that we can rely on to tell us what the temperatures were a long time ago. And this is CO2 over time, and this is the last million years or so. You can see that the carbon content was actually pretty low compared to now. Right now we're up here. It's increased dramatically recently. And through most of the Earth history, it was below the 1950 level. And it's gone way up. Yeah. Oh, well, it has to do with carbon emissions, of course. Well, the previous events, I don't know. I don't know why it went up and down.
Why was the temperature so high for such a long time?
Because carbon was, well, fairly high. And, yeah, I don't really know, to be honest with you. But,
There was
It's-
other volcanic gases too, sulfur
that's true,
dioxide.
yeah, yeah. This could be from lava flows, because a lot of times lava flows will emit different gases. And they may have emitted carbon dioxide, causing the concentrations of carbon to go up, and therefore, well, I have a slide here in a couple minutes. It shows you the relationship of carbon dioxide and temperature. But our carbon concentrations we can figure out from ice cores from more recently, and then from soils and fossilized plants. Plants have these little things called stomata, which are little nodules that allow plants to breathe, and particularly carbon dioxide. And if you have more of those, then you have higher carbon dioxide. And this is the relationship of carbon dioxide and temperature. And you can see the dark color is carbon dioxide concentrations, and the lighter blue is temperature. And you can see it's a pretty darn close relationship, pretty strong correlation. So if people say there's no relationship to carbon emissions and carbon concentrations and temperature, I don't think they're right. The evidence, the data does not support that. And extinctions, as it relates to climate change, most extinctions are because of climate change. And the big extinction event was back in the Permian, which is about 250 million years ago. And they had flood basalts, which is like lava flows, and they had carbon dioxide and sulfur dioxide that were emissions, and caused the CO2 concentrations to go up, and then the temperatures increased, and therefore you had a lot of extinctions. You actually had 57% of the species died out. And when dinosaurs died out from a meteor impact, and you had dramatic cooling of the atmosphere, of the Earth, because of the high concentrations of particulates high in the atmosphere, and it caused cold weather for hundreds of years. And 75% of species actually died in that event. Oh, yeah, go ahead.
Under dinosaurs 65 million years ago, I see the cause being meteor impact. Under
Yeah.
the Great Extinction, the Great Dying, I'm wondering what the cause was of that. I see
Oh.
the evidence of it in the, 57%, but why did
Oh,
that
well,
happen?
very cold temperatures had nuclear winter, effectively, for several hundred years. And dinosaurs died out, the big creatures died out, but the little ones, which mammals, eventually us, were small and could adapt better.
I think the question was about the prior one, which was the Siberian traps and
Yeah,
the other
That's right.
volcanic activity. Incredible
Yeah,
volcanoes that erupted for
the
millions of
lava
years.
flows covered a large area.
Was that 250 million years ago eruption? Does that include the like Yellowstone supervolcano eruption?
No, but it could now.
Yeah, these things made the Yellowstone supervolcano look like a firecracker. But they were basaltic flows, they weren't explosive, and they just continued for literally millions of years.
Right.
Lava and outgassing, and it changed the climate.
One thing about Yellowstone is it could blow one day. If that happens, it would probably wipe out several states. So it'd be, don't go to Wyoming. Although it's every several 100,000 years it might happen, so we're probably good for a while. And one thing to keep in mind too is that these previous extinctions, the climate change, the warming, increased very gradually over millions of years. So species, even though a lot of them died out, they had a time to adapt. And they could adjust to the temperature and the changing climate. But what we have now with the rapid change, maybe not. And I thought this was kind of an interesting concept. One thing with the the meteor, you had iridium associated with the meteor, and that had a deposition all over the Earth at the time. And you had this little layer, less than an inch, of iridium rich, all over the Earth. So that kind of demonstrates that the meteor, in fact, was the cause. And that's just kind of a list of causes for extinctions. Meteor impact, volcanism, with carbon dioxide emissions, other carbon releases by humans or whatever. And then the reason they died out was from direct effects from dying from the heat and habitat loss. And one thing too, keep in mind, besides climate change, loss of habitat is a big factor in extinctions, at least currently. Because like the Amazon rainforest being plowed over and cut down, you lose habitat. When you lose habitat, you lose species. Near us, for instance, out in Aurora, we had a little, like a bushy area that they cut down. And my wife was upset. She goes, yeah, they ruined the habitat for all these little critters. That's a small scale. And this is a temperature recently, and since like 1880. But you can see the temperature is increasing very rapidly. And that's when some people say, well, we've had warm periods in the past, and, not that unusual. Well, in the past, you never had an increase this rapid. It's very, very fast change since like 1950.
That's a centigrade scale on the side.
Yeah.
That's centigrade scale?
That's right.
1 degree or so since the
Yeah.
1880s.
And
One and a
they're
half.
talking in terms of reducing the impacts, keeping the increased temperatures below 1.5 degrees centigrade. But I don't know if that's going to happen. Anyway, what will the future bring? Well, we're not quite to the tipping point, which means a point of no return. Not quite there yet, but we will be if we don't change things. And the estimate is that 1/3 of species will be extinct by 2030 or 2050. And it's inconvenient. That's all I can say. Al Gore had a series of talks called The Inconvenient Truth. which he talked about climate change. And what time is it? That's it. If there are other questions?
You were talking about an erratic boulder. The first time I ever saw an erratic boulder was in Madison, New Hampshire. And the
wow.
Great Madison Boulder, it's the size of a large colonial house. It's 3 stories tall, more than 60 feet in length. You
Wow.
climb on top of it with a ladder. And it's strictly an isolated hunk of granite. There's nothing around it. And evidently it came from Maine, from the Appalachians up in Maine,
Yeah.
and managed to get down to the
And you
southern
can
New
get
Hampshire.
big boulders, they're called erratics, from
Yeah,
glaciers.
erratics.
Glaciers will dump a big rock, you know.
When boulders go on vacation, right?
That's right. Yeah.
So, are you familiar with the 26,000 year cycle of the precession, orbital precession?
The what?
Due to the orbital precession of the Earth, the 26,000 year cycle?
No, not really.
So, like, you know, you spin a top and it spins quickly, but then the axis of rotation
Oh, yeah, the
goes
Earth.
slow.
Yeah, yeah.
And so the Earth does. Do you know how much, because I've kind of heard different things about how much of an impact, like pre-anthropogenic, like, you know,
Yeah.
over the course of millions of
Well,
years, how much does that affect the
Very little.
climate?
Very little.
Very little?
Yeah.
Okay.
Like less than 1% probably. Yeah.
So Bill Gates was getting a lot of criticism lately because he was talking about we should really just spend our time mitigating against climate change and spending a lot of our other money against poverty and disease and everything. What's the thinking now behind the difference between doing something about the core problem or mitigating because of the results of it?
Well, my opinion is take care of the climate first. Because all these other things will be that much worse. And there are things you can do to counter some of the climate changes. Geoengineering, but they're very risky because we really don't know what the overall end result will be. For instance, you can put a lot of particulates high in the atmosphere and reduce the sunshine coming through, but we don't know really what other effects that might have. But in terms of spending money, I think you'd be way ahead spending money on reducing climate change. Things like renewable energy, stuff like that. And there are things you can do like that that really aren't going to cost you that much, but it's going to have a really good result in the end. Well, like green energy, it's more efficient actually than like coal and other things. Anyway, and they talk about natural gas being a better energy source. Problem with that is, it's true, natural gas emissions are much less carbon dioxide, but to produce it at the oil wells, you emit a lot of other gases and other bad stuff. So there's no really easy solution to energy.
I noticed that all of your graphs have focused only on CO2.
Right.
And I also noticed they all went, interestingly, back 800,000 years.
Well, yeah, most of
which
them,
is,
yeah.
Which is how deep the ice in Antarctica is. But you've, I think in this, ignored the fact that there are multiple greenhouse gases.
Yes.
You mentioned methane.
Right.
Methane's
Methane's a big one, yeah.
Methane is significantly worse.
Oh, yeah,
than
40 times.
CO2.
Yeah, 40 times.
The nitrogen oxides that occur from the oxidation of probably the anhydrous ammonia that gets dumped on essentially all of the farm fields, at least in the Midwest, also are relatively potent greenhouse gases. So when you look at the past and you say, why is the temperature high but the CO2 isn't following it, is there's a boatload of other possibilities that
That's
you're
true.
just not mentioning.
You're right, it's an oversimplification, that is true. But you're right, methane is a big factor. in terms of like cows, that kind of thing.
It's destroyed in the atmosphere pretty quickly.
Oh, methane is?
There's some questions about tipping points as well, too, that we can say that this is just a little bit more, this is a little bit more, but somewhat relevant back to your talk about the snowball Earth, too. Once you get to certain tipping points, you aren't changing things.
Yeah.
And those are estimations, too. Scientists say, here's our estimation, but you know, the concept is a reasonable concept to say, if you have something in your house that keeps your thermostat going higher, as the temperature goes higher, your house is going to just keep getting hotter and hotter and hotter and hotter, and the same thing can happen in a planet,
One I glossed over, I didn't talk about the feedback effect.
right?
I mentioned it with the snowball Earth, in that once you have things getting warmer, and then the glaciers over the land, that melts, then you have lower reflectivity, and therefore, you have higher temperatures.
Yeah. The tundra in the far
yeah.
north, when the tundra is snow-covered or ice-covered, it has a lot of reflectivity. But when the ice melts and there's nothing there, it's just the dark earth, then that's all absorbing, and that's a feedback loop
And the
that's very
tundra
negative.
itself has a lot of CO2.
Yeah, and it releases all that then.
Right.
Yeah,
We're in trouble.
permafrost, right?
Yeah.
One point I don't think you pointed out, because you saw the ratchet of the temperature going down up in the last
Yeah.
800 years. What scientists believe is a bootstrap method, where we're in glacier places, and you got the tipping moving a little bit, and it only affects it maybe 1/10 of a degree, but it heats a little of the earth, melts a little snow,
Right.
heats it up. That goes on, it heats up the ocean a little bit, which now releases CO2,
That's right.
and then it comes back again, and then, so now you have more temperature, so you got more
Right.
melting. And that's why CO2 slightly follows the temperature, because it's not so much the difference of the tip, 'cause that's, like I said, that without the loop would only raise temperature about 1/10 of a degree. The other thing you gotta remember here, I mean, we're looking at 1.5 degree rise.
Right.
Well, that's an average, which
That's
3/4
true.
of water is water. Most of the land mass is in the northern hemisphere, and so it's already up to 2 degrees. So it's gonna warm up a lot quicker here in the north than it is on the ocean, or what the average is gonna be.
Well, I tell you, if I were younger and had more money, I'd be buying real estate around here. Because I think people from the south, they're gonna get tired of 100-degree days, and they're gonna be wanting to move up here.
Well, I'm looking at Alaska.
Even better, yeah. And they're gonna want our water. I'm not giving it.
No, there's a lot of implications for all this, right? That
Well,
you try to look at it in ways, and you try to put it into a perspective of what's going on nowadays politically. And, you know, we had Mark just 2 weeks ago talking about the Citizens Climate Lobby and what their priorities
Right.
are. And are their priorities the same as they were or would be if a different person had been elected president? Or, you know, how do we handle what goes on now? And I think
Yeah.
it was interesting to me to hear him say that although he's still optimistic and feels like he's ready to take on and try to change the world for the better, for right now, I think maybe the Citizens Climate Lobby has some different perspectives of
Yeah.
what do you do for the next number of years about this all, and not tear yourself up, not butt your head against a wall that isn't going to move for you, but prepare. And I think his basic point was, I think he wanted to improve the grid, the electrical grid around the U.S., so that we can handle all the electrical needs, and still start talking about exactly how we're going to get power to people, you know, and be ready to do that when the time is ripe.
yeah, because you have West Texas, where I lived for a while, and you have a lot of potential there for solar energy, but the problem is getting that to market. you have to have big power lines.
Right.
So it can be done, but it takes a commitment, which I don't think we have right now politically. I mean, some people say it's a hoax. Well, the facts don't support that. I mean, you look at the geologic record, it shows there's definitely times in the past where you have had warmer temperatures, but then you'd also look at the CO2 concentrations and temperature. You saw the graph, like, they overlay each other pretty much.
Yeah, and I think, again, going back to those tipping points and those feedback loops and some things, after they run their course for a while, like a lot of lava flow that brings out a lot of CO2,
Right.
then that magma chamber in that area is exhausted, it drops down again, and so then there's things
Yeah.
that bring things back to an equilibrium. We've been living on a pretty wonderful planet that has had a very sustainable equilibrium, or we wouldn't be here talking about it right now.
Well, you saw the one slide, it showed that we're actually in a glacial period right now. I mean, it's colder now than it has been in the past.
Yeah,
So,
yeah, that was surprising to see.
yeah, I was surprised when I saw that.
Yeah.
I thought, wow.
But to me, it seems like we have to say that you have to realize these loops and there, the Earth is a fairly self-sustainable planet.
Yeah,
You know, Mars was a very self-sustainable planet, we're starting to find out for quite a while. Sooner or later, it hit a tipping point in what it did, and it didn't have people around apparently to cause that, but we're definitely impacting our
the
planet.
Earth will correct itself, but it may take millions of years.
It may shake us off like some bad
And
fleas.
in the meantime, there'll be extinctions. It could be us.
Yeah, you mentioned about the times in the past when the Earth was much hotter. That was before there were humans or hominids around. I
Right.
think it was beyond 6 million years ago. Other than heat, what was the forecast right now is kind of a whole lot of desert, especially inland, if the heat continues to increase. What was how much is that what we had on the Earth? Do we know?
I'm not sure, to
We
be
must know.
honest.
Do we know? Was there just deserts everywhere, or was
I'm
there?
not sure, but we did have a lot more water, a lot more like ocean environment. Yeah. Less land, more ocean.
Some of that back then, at one point, all the land was together.
Right.
Millions of years.
Yeah, in fact, one reason some people think the snowball Earth occurred partly was because all the continents were grouped up. Big supercontinent called Pangaea. And because of that, it caused colder temperatures because it was more at the equator. I'm sorry.
I forget what I was going to say. The other thing we got to remember is temperature rise will not be linear. There will be spikes. Things will happen where it'll go up. Like, for instance, when the polar ice cap melts, all that heat that used to get reflected now is going to get absorbed.
You're right.
And I've heard as much as 15 to 20% or 20 degrees within 1,500 kilometers of the land, which, as we talked earlier, will start melting the permafrost and whatever. And the second point on that is, because we're talking about desertification, the basic weather patterns is things heat at the equator and move up
Right.
to where it's colder. Well, that colder spot's no longer going to be the North Pole, at least in the summer, it's going to be over
Right.
in Greenland. So all those weather patterns are going to shift, and you're going to get
Yep.
cooler, or you're going to get drier air than coming up over the U.S.
Well, the other thing is if you melt the glaciers on land, then you're going to get an increase of water in the oceans. Now, if the glaciers in the oceans melt, it doesn't really matter.
No, what happens is,
In terms of the water level. But if it melts like on land, like in Antarctica, then the oceans are gonna get a lot higher.
Things that have been happening in Antarctica are some of the ice shelves that are
Yeah.
hanging over the water. Some have broken off,
That's
some
right.
are in catastrophic shape, and they're talking about what'll happen with them, and that is a problem in some
Yeah,
essences.
and that can happen suddenly.
Right, and that's the point I was going to make too. Then they also are acting as a dam that stops the ice that's kept over land from
Right.
sliding down into the ocean.
Yep.
And like you say, this can happen catastrophically if things occur that don't stop the ice from staying on top. It's happening in Greenland, it's happening
Yep.
in Antarctica, and significant
At the bottom of
potential
glaciers,
problems.
you have kind of a watery slush, and that causes things to move more quickly.
It's almost like a lubrication system on there
Exactly,
to
yeah.
let it flow. Yeah. Is there any good news?
Well,
You said earlier that the temperature is good, it's getting colder here, right? You said the temperature is getting colder?
no, I'm saying, I said we're in an ice age right
Yeah,
now,
yeah.
generally. But that trend is reversed. It's not going down. I wish it were. But we're definitely having an increase in temperature. Is there good news?
That's a
Well,
great
yeah,
point.
people are waking up, I hope.
People are waking up, yeah. And I think 2 weeks ago, we heard some
Yeah.
good news, I think,
Yeah.
with the Citizens Climate Lobby. If you're looking for participating and giving some help, the Citizens Climate Lobby is a great organization. It's looking for nonpartisan solutions to climate issues. They look for people from both sides of the aisle to work together. They look for situations that are definitely not partisan. And there's people involved in this church in it. I was involved with it for a while, and Mark Ailes is a guy, if you know him, and I can get you in touch. If you want to talk to me, I can get you in touch with those people. But yeah, I think it's a challenging time. We wouldn't be talking about it for the last 20 years if it wasn't a challenging problem, you know, and it's kind of frustrating to maybe get poo-pooed about it for so long. You're a geologist with 26 years of experience with the U.S. government and the EPA and 10 years or so down in working in oil and gas
Right.
structures,
Yep.
helping people find the oil. It helped our economies go and everything like that. So when you have things to say, it's very valuable to hear the points that you're making.
Oh, thank you.
And we appreciate that very much, yeah. But then it does seem to be something that people have to do things about.
Well, people have to believe in science. A couple weeks from now, maybe we can talk about things that science has gotten wrong, but in general, science is a good tool to help people understand what's going on. Go ahead.
If we're in an ice age now, why is the glaciers melting?
Oh, well, in general, we're lower temperatures. However, that's changing rapidly. It was going down for a long time. Now it's not going back up.
I think, wasn't it like 60 or 80 years ago, maybe you know, Scott, that they were talking, scientists were talking about the challenge of global cooling.
Yeah.
It was going to get too cool. And, you know, as you say, science is a great way to solve a problem, but that doesn't mean it knows the answers to all the
Right.
problems. It's a technique. It's a
Well,
method to
one
solve
thing
problems.
People don't understand, a lot of people don't seem to understand about science, is it never gives you a definite final answer. It gets closer and closer to the truth, kind of asymptotic. It gets closer and closer, but it never quite gets there. It's always available to reevaluate.
Right. And as you get more data and get more information,
Right.
then you have to incorporate that into the topics that you're studying.
That's right.
And yeah, I mean, there's a lot of hypotheses and thoughts and ideas about everything, and science is one way to solve those
One
things.
thing geologists are good at is coming up with theories. It doesn't mean they're right, though.
Asymptotic. Have you ever heard of that, Scott?
Asymptotic. It gets closer and closer, it never quite gets there, though.
So my question is about the chain of life in the oceans from which we all benefit. And since the ocean is a carbon sink and it changes the pH of the ocean, and life in the ocean from the top going down from the small creatures to the large
Yeah.
creatures, which we eat and live on, is there a difference in, when you're talking about tipping periods just generally, as you have, is there a difference in the tipping period of this chain of life in the oceans from which we all benefit while carbon is sinking in, pH is changing, and life in the oceans is changing?
Yeah, you're right, that's a big factor. In fact, if you look at corals, they're dying. That's not a good sign. Because I remember when I was in grad school, we went down to the Florida Keys. It was really cool. The corals were really spectacular, but they're dying off now. And that bodes ill for us and for the oceans. Because you're right, more acidic, higher temperatures. Go ahead. Say.
Yeah, I was just going to reiterate that, yeah, the higher carbon CO2 in the atmosphere, whenever you have any water exposed to, in a CO2 environment, it starts to form carbonic acid, right? And so
Yep.
that's going to happen too.
Yeah, the oceans are getting warmer too.
When you think of life in the ocean, whales are eating, many certain types of whales are eating just tiny plankton, microscopic plankton, but massive amounts of it. And those things are all suffering now because they can't form. I think the calcium doesn't form properly in their exoskeletons
Yeah,
and so on.
if you destroy the base of the food chain, the higher organisms aren't going to do well.
Yeah, yeah.
So my question was, is there a difference between the tipping point in that and the overall tipping point that we're talking about for all of us? The tipping point of life in the ocean
Oh,
and the food chain, or is it the same?
well, the oceans, you don't have the feedback loop in the oceans, but the feedback loop, the cycle of increased temperatures can affect the oceans. But the oceans itself, I don't think would have a feedback loop in the ocean itself. But still, it's a big deal, the oceans. The health of the oceans are really important. Yeah.
It might be valuable to point out the difference between a positive and a negative feedback loop.
Yeah.
A positive feedback loop enhances the effect, amplifies it. That's like a microphone feedback if I were to bring this over by a speaker. And that's a positive feedback. A negative feedback is a dampening effect. The stronger something happens, the stronger the dampening tendency. And many of Earth's systems have different actions in terms of feedback. Some are positive feedbacks, like the warming of the Arctic causes a release of more greenhouse gases, which causes more warming, which releases more gases in the Arctic. So the Arctic is warming up more rapidly, seeing more effects of climate change than nearly any other place on Earth. Then you can also have negative feedbacks. You get warmer atmosphere, you get more water. If you get more water, then the water in the air can absorb more CO2, acid rain essentially, but then that also washes onto the ground, it causes erosion of rocks, it changes the geochemistry of erosion and deposition due to erosion. So there's all kinds of complicated feedback cycles. One of the reasons the climate modeling is so difficult is because it's not just one thing. It's not just carbon dioxide, but the correlation, as you showed, the correlation between carbon dioxide and temperature is so profound that it looks causal. One of the lessons of science is just because you have a correlation, it doesn't mean that it's causal.
Right.
You have to look for a mechanism. So that's why they do things like experiments with lasers. You can create a laser light that's, the color of light is absorbed by a glass or a chamber of CO2. Well, that light color is infrared, right? And it's infrared radiation. The sunlight hits the Earth, it heats the Earth, the light comes back off of the Earth in the form of infrared radiation. But infrared can't get through CO2. right? So it's all these complicated processes and many both positive and negative feedbacks that's hard to untangle to understand what's
Yeah.
really happening.
And one thing, erosion of rocks causes carbon dioxide to be released.
Okay.
That's one thing with feedback from the snowball earth. That's one thing that helped melt the snowball was you had more erosion. Therefore, you released.
Yeah, you didn't have more, I don't know, more erosion while it was covered with ice?
Releases carbon dioxide.
The volcanism, what I'd heard
Oh,
is this.
both.
Yes, snowball Earth ended because of volcanoes outgassing and that,
To a large degree, yes. But there's also erosion
yeah,
of rocks, which release CO2.
okay.
Pardon me? Yeah, limestone, yeah.
Right.
Basically, yeah.
Well, thank you so much. I think that was
welcome.
nicely done. Nice presentation. Appreciate it. If anyone, this was nice. Jim came up and talked to me, I think just 4 weeks ago, and said he'd like to give a talk. And so he prepared it and did this. So thank you very much. It's nice to do. That's
Thank
what
you.
we like, this community of sharing science background. I'll never have 26 years at the EPA in my repertoire, so it's very good to have other capacities. And thanks very much for stepping in. And others that want to step in and talk, I know we've got people in here that have talked before. Scott has, and Robert has, and different people too. So, Ray, you're planning one, I think, coming up. Putting him on the spot, yeah, putting him on the spot. So, and Lori, you plan on talking one too. So that's what's nice about this. Keep coming in, keep coming to Science Sunday. We really appreciate it. It was a real nice turnout today, and we hope that you keep coming and enjoy it. We've had a lot of nice talks from a lot of people. So we thank the church and the community here that we're all part of, and I think this is a real great way for us to kind of focus in on what we want to do and how we want to change the world. So thanks for coming.
Yeah, thank you.